Hi everybody. In this video I'm going to introduce the idea of a linked list. So I'm going to talk about what a linked list is and how it's similar to an array list or an array, how it's different when you might want to use it, and we'll also in that process see some of the beginning implementation details. Let's start by thinking about an array list. So for right now, just think about an array list simply as a tool for storing Java objects. Think of it as a place to put objects in so you can get them back out later. Forget about the specific details of what exactly an array or an array list is or how it works, just its basic function. So with that in mind, what are the fundamental operations of an array or an array list? Well, in both cases, the two fundamental operations are get and put. Put some data into the array, and then you get it back out later. It's just storing data for you. Now, if you're focused specifically on an array list, you get some more functionality. So what are some other common operations you would do on an array list? Well, if you think back to what you've done in CS1, you probably called the add method at some time or another, put data at the end of the list. You might have taken data away from the end of the list, so I'll say remove tail just for simplicity. Not quite as common, but you can also insert or remove data from any arbitrary spot in the list. You can stick some data right in the middle of that list if you want. There's other things you can do as well, but this covers sort of the basic stuff you would do with an array as a storage container. So now, what's the running time of each operation? How long does it take to do all of this stuff? Well, get and put are both constant time in arrays or array lists. You just say put the data in there. Now we can start thinking about the details of how it works. An array is a bunch of slots in memory, so get and put, you just take the data and you stick it in the corresponding slot in memory, slot 0, slot 1, slot 2, and so on. If you want to add to the end of the list, that's also pretty easy. You just keep track of where the end of the list is and you stick the element in the slot. Removing from the end of the array is also just as easy. You just pretend the array is one element shorter. So you mark that slot as unused. Now where it gets a little more difficult is if we want to insert or remove not at the end, but anywhere in the array. Well, those both take time big O of n. It's linear. If there's 100 things in the array and I go stick something somewhere in the middle, because the array is just this list of items, everything toward the end of the list has to shuffle down by one. Or if we pull something out of the middle, we have to shuffle it back up. We can't really have empty holes in the middle of our array. And this works well most of the time, right? This is what we use throughout CS1. And so if you're doing something where you're mostly using these big O of 1 operations, putting stuff in the array, getting stuff out of the array, or just sticking stuff at the end, it's pretty efficient. But if you happen to have a slightly different application where you have to put stuff in the middle of the array, you'll notice the performance hit. So think about this. What if you're constantly sticking stuff into the middle of the array, and let's say you have n items you're putting in the array? What's the big O running time? How long will it take to do those n insert and removes? Well, it'll take in total big O of n squared, because each thing you put in the array will take up to time n, because you might have to push everything else down, and you're doing that n times. So n times n is n squared. So where might this happen? Right? You might not have run across this in the types of projects you've done so far. So let's think about a hypothetical priority queue for closed class permits. So some of you probably wish we did this already, but let's pretend that we give out our closed class permits in some sort of priority order. Maybe students closer to graduation get permits first, so that it's not necessarily first come, first serve. And to keep things simple, let's just say for right now that when somebody comes to Lindsay, who's our admin, and asks for a closed class permit, they either go to the front of the line or the back of the line. They either have some sort of priority, some sort of urgency to get into the class, so they get to go to the front of that list, or it's just a regular student. Hey, I want to take Woodering's class because he's such a great professor. Okay, well, you gotta just get in line. And so now, let's think about what that would look like if we just used a regular array. Okay, so here I have just a plain ordinary array. And let's say student 1 comes along and asks for a permit. Only student goes to the head of the list. Maybe students 2 and students 3 come along, and we just add them to the list. This is pretty easy. But now student 4 comes along, and student 4 has priority for some reason, right? This is the one class he needs to graduate, so we're going to make sure he graduates. Well, we want student 4 to go to the head of the list. Well, with a regular array, the only way to do that is we have to push everything else down. We have to move S3 down a slot, and then we have to move S2 into S3 spot, and then we have to move S1 into S2 spot, and now we can insert S4. Okay, and then this continues, right? We have some number of regular students come along. And then at some point, a student will come along again with another urgent case, another reason to be put at the head of the list. And of course, to make this work, then we're again having to shuffle everything down. We have to move S7 down, S6, S5. Pardon me for not taking the time to erase all that. And then finally we can put S8 in there. All right, so if there are n people in line already, then inserting at the head takes big O of n, right? Everybody in line needs to move down. So in the worst case, let's say every student who walks in the door has the most urgent case. So this doesn't actually happen in real life, but it helps us think about the process. If the students somehow manage to come to Lindsay in just the wrong order, where the most urgent student was always the last one to walk in the door, to handle n students would take big O of n squared, right? Big O of n times n. And so we think, well, maybe we can do better than that. But notice what's going on here. And why the performance overall is so bad is because we're focused on those slowest operations, the insert and the remove. Now let's think a bit for a minute why insert and remove are the slowest operations when we deal with an array list. Right? It's because arrays focus on position. When you're dealing with an array or an array list, you really care who's first, who's second, who's third. That's the job of the array, is to know exactly who's in what spot. Right? When we had this over here, we had S8, then 4, and then 1, 2, 3, 5, 6. But in this application here, where we have this priority queue, we don't need to know, for example, who's in position 5. If you go into Lindsay and say, who's 5th on the wait list, it doesn't matter to Lindsay who's 5th on the wait list, right? What matters is who's first, right? Who's getting that first permit, and then after that, who's next. Right? It doesn't matter who's 5th. We just have to be able to keep track of what order people are in. Now, an array certainly does that by keeping track of precisely who's 1st, 2nd, 3rd, and 4th. The consequence of that is then you maintain the order, but you're also maintaining extra information that you might not need. And that's why trying to insert somebody at the beginning of the list takes so much time, is just by putting the person at the head of the list, you have the information you need, who's first and who's next. But then you also take time to adjust who's now second, who's now third, who's now fourth, who's now fifth, and that just doesn't matter in this case. So the purpose of a linked list is to say, well, if we don't care precisely who's first, second, third, fourth, fifth, and so on, if we just care who's next, what applications get faster? So let's try this idea out. So now, instead of using an array, we're going to maintain the queue this way. And it's a bit of an analogy, but follow me for a minute. So this will be Lindsay, the keeper of the list, and a student comes in and says, I need to be put on the wait list. So Lindsay just writes down his phone number, the phone number of who's ever first. And this student might be student 1. That's all Lindsay needs. Lindsay just needs to know who's first. And it turns out she also needs to know who's last. So right now there's only one student in the list. That student is both first and last. So when it comes time to handing out permits, Lindsay calls the student and says, okay, I've got a permit for you. Another student walks in now. So student 2 comes in, says, I need a permit. No urgency here, no special treatment. So now all we have to make sure is that we know that student 2 follows student 1. So Lindsay calls the first student. She has his phone number right here. So she calls the first student and says, when I give you your permit, remind me that student 2 is next in line. She doesn't need to know who's next in line until he comes to the front of the list. But because the student came to Lindsay, she's also going to remember who's last. So this student's now last in line. Okay, so student 3 comes along. And it's the same thing. This is a typical student. No special treatment is in order. So Lindsay knows who's last in line. Student 3 is now going to be last in line. So she calls up the student who's last in line and says, when you get your permit, remember who's next. And as before, then she will remember who's last in line. Okay, so far there's not a big difference here. I should have saved some more room in the drawing. Hang on one second. Okay, so student 4 now comes along. Student 4 does have a reason to go to the front of the line. So what Lindsay can do is she can say, all right, you're now at the front of the line. And so she tells student 4, all right, I know who was at the front of the line. You're now at the front of the line. So after you get your permit, you call student 1, and then she remembers who's at the front of the line. So now we are able to put student 4 at the front of the line in a constant time big O of 1 operation. We didn't have to shuffle everything down, right? We were able to put student 4 at the front of the list, make sure Lindsay knows who's at the front of the list. We made sure we knew who was next in line, but we didn't take the time to adjust all the indices. Whoever was third is not now marked at fourth, and fourth isn't marked as fifth. We skip that because we just don't care. All right, and student 5 can come along and we'll do the same things we've been doing, right? Lindsay calls the student at the end of the list and says, when you get your permit, you got to call student 5, and she will also remember who's at the end of the list. And this can go on. We can add to the beginning of the list, we can add to the end of the list, and it's all constant time. And so if we're handling a list with n students on it, we now have the benefit of being able to handle all n students in time big O of n, instead of where before we had to do n squared, which adds up to a lot of time if you have more than just a few students. So that's the big idea of a linked list. Instead of keeping everything together in memory next to each other, where you're implicitly remembering who specifically is first, second, third, fourth, you just remember who's next. and then you can insert and remove things without taking extra time. Actually, let's talk about remove for a second, right? When it comes time to handing out permits, maybe a slot or two comes open. Lindsay knows who's at the beginning of the list. She calls student 4, says, here's your closed class permit, and by the way, who's next on the list? And he says, oh, well, student 1 is. Here's his phone number. So Lindsay will update her information, right? Student 4 is not here, but before he leaves, he tells Lindsay that student 1 is next in line. So she just updates her data like this. And so now we can hand out those permits. We can remove stuff from the beginning of the list as well in constant time. We can also extend this story. So what I've described thus far is called a singly linked list, where we just keep track of who's next. But we could also do a slight variation on that, called a doubly linked list, where you not only keep track of who's next, but you also keep track of who's before you in line. So when you get in line, you exchange phone numbers both directions. And now, the cool thing about that is you can take yourself out of line. So if student 3 decides, hey, I don't need this anymore, or I got into another class I was waiting on, student 3 now has the option of calling student 2 and saying, hey, oh, by the way, I'm done. I'm getting out of line. Instead of calling me, call student 5. So student 3 can get out of line, and as long as he uses that backward link to call student 2 and say, hey, I'm done, call student 5 instead, you can remove anything from the list also in constant time. Okay, so to summarize, if we switch from an array list to a linked list, what we've done is we've swapped the slow operations. With an array list, the slow operations are the insert and the remove. With the linked list, the slow operations are the get and the put. Because you can't just say, get me the 6th element in the array. We haven't kept at our fingertips which array is 6th. And the only way to get to the 6th element is to start from the beginning and follow 6 links. Ask the first student who's the second, ask the second who's the third, and so on. Likewise with the put, I can't say, go put this in the 6th spot. I can say put it after somebody. If I already have the phone number to a particular student, I can put a student in line after anybody I want. But to say, give me the 6th student or make this the 6th student, you have to walk down from the beginning of the list. So both store data for us, and in particular, they store data in order. There's a concept of first, second, third, and fourth, but which operations are faster have changed. So now when you're writing a program and you need a list of data, you can think about how am I accessing that list? And I can choose the data structure or the tool that will be faster for my particular application. Okay, so that is it for the introduction. In the next video, we'll start writing some Java code to actually implement a linked list.